Okay, so you all probably know how to compute the average of a finite set of numbers, right? So for instance, if you're given 5, 7, and 9, then to take their average, you just need to add the three numbers up and divide by 3, which is the number of objects you've added up. And here you'd get 21 over 3, which is 7. Right? And so 7 here represents a measure of central tendency here, right? It's kind of the center or the middle of your group in some way. Although there are other measures of averages that I'm not going to talk about. This is specifically called the arithmetic mean of these three numbers. And it represents a middle ground in the sense that if I draw 5, 7, and 9 as sets of points, like this, like sets of circles, we have 5, 7, and 9 here. You can think of the average 7 as what you get when you try to level this off, right? When I take these 2 points over here and put them over here in the first column instead. Right? And so what I've obtained here is now 3 columns all with size 7, just by transferring those two, which tells me that 7 is the average here. Right, so what we want to do here is we want to extend this notion of the average to functions using an integral. And the idea is very similar, right? Instead of now taking a sum of a finite set of numbers, well, what if you had a function, whatever, it could look like this, for instance, y equals f of x. And what if you wanted to take the average of all the values of f of x in the interval from a to b? And here you would probably complain and say, how is that possible? There are infinitely many real numbers in between a and b, right? So we can't add infinitely many things up and divide by infinity to get the average. Well, it turns out we can, right? That's exactly what this integral is doing here. Remember, this integral from a to b of f of x dx can be thought of as an accumulation of infinitely many, infinitely thin line segments that constitute together this area under the curve of f of x. So if you think about it in this way, then now you can just divide by b minus a, which is the length of this interval, right? And this corresponds to dividing by the total number of elements you're adding up. But in this case, it's a measure of, well, the width of this interval. So I'll give you an example with a specific function here. Let's say it's the function y equals cosine x, right? Or f of x equals cosine x. So we know at pi over 2, it's at 0. At 0, it's at 1. And now let's ask the question, what is its average value on the interval from 0 to pi over 2? Okay, so just looking at the graph here, what would we expect it to be? Well, clearly it's going to be a number in between 0 and 1. Right? Because your function values are all in between 0 and 1. That means we can't have an average that's larger than 1 or negative. And you can probably also guess that the average is going to be larger than 1/2. Simply because this curve is what we call concave downwards, right? And it's slow to decrease at the beginning and then faster to decrease at the end. And what that means for us here is that for the most part, it's going to be more than half for the function value. Okay, so what do we actually get here? Using the formula, again, think about this integral as adding up these infinitely many objects, right? And 1 divided by the length of the interval, pi over 2 minus 0, corresponds to dividing by how many objects you have, right? I mean, that's how you can think of it, although technically that's not exactly what this is. But yeah, so now this is 2 over pi, and this is now sine x evaluated from 0 to pi over 2, which is just 1. So this is 2 over pi, or slightly smaller than 2/3. And if this is 2/3, then that means the average value is somewhere around this line. Okay. And if you remember our imagery from the previous slide of these extra dots going over to fill in the empty spaces in the first column to make them all level and equal, well, we can do the same thing for average value. If I draw this rectangle here with constant height at 2 over pi, I can also imagine this as my average, because it's pretty much getting this portion of the graph that's above the average and saying that it's actually exactly enough to fill in the gaps here for the parts that are smaller than the average. Right? Again, kind of like taking 2 from 9 and giving it to 5 to make everything level at 7. Right? So the same thing's happening here. We can take the area, cut it off, and put it in here, right? I mean, it's not exactly the same shape, but they have the same area here. Okay? And so, let's look at another example. So here we're given an application type question. Right? It's the velocity of a particle is known to be t squared plus 3 meters per second for t from 0 to 3 seconds. And part A here is something you've seen before when we talked about net change. What is the displacement as of 3 if the particle started at position 0? And so we know from the net change theorem that the integral of v of t dt from 0 to 3 is equal to s of 3 minus s of 0. Right? And so what we do is simply, well, let's evaluate the integral. Integral of t squared plus 3 dt is 1/3 t cubed plus 3t, evaluated from 0 to 3, and this is 9 plus 9, or 18. 18 minus 0 is still 18. Right. And so now this is equal to, now this is by the net change theorem. Right, and so what we have here is that s of 3 is equal to exactly 18. Right, because s of 0 is 0. Okay, so that's the displacement. Part B is a bit interesting here, because it talks about two averages, right? First, the average velocity of the particle on that closed interval. Second, the average value of the velocity function, so that they're equal. And now you may be thinking, wait a minute, isn't it pretty clear here that these will give you the same number? Aren't they the same thing? Average velocity, average value of the velocity function. And yes, well, it might seem to you like we're splitting hairs here. And in fact, they are always equal to one another. But the way we've defined them is different. Right? What is the average velocity? How is it defined for us? So the average velocity of the particle is equal to the change in displacement over the change in time. Right? That's how you can compute the average velocity. And on the interval from 0 to 3, this is s of 3 minus s of 0 over 3 minus 0. Right, so this is 18 over 3, or 6. How about the average value of the function? So the average value of the function v of t on the same interval from 0 to 3 is, now we're using the average value formula, 1 divided by the length of your interval, integral from 0 to 3 of v of t dt. And we've done the exact same integral up here, right? So I can just plug in 18 for the value of the integral to get 6 meters per second as the average value of the velocity function. And the reason why these two quantities will always be the same, well, regardless of which interval I'm taking, right, is because of the net change theorem, right? So the net change theorem says that this quantity here, the change in displacement on top of your fraction, is always going to be equal to whatever this integral is, while that 3 minus 0 term is there on both the left and the right. Right, so then we've shown that the average velocity is always going to be equal to the average value of the velocity function. And so let me just end here by talking about the mean value theorem for integrals. And you may remember seeing a mean value theorem in your differential calculus course. The idea here is pretty much the same, in that it talks about the existence of a certain number. It doesn't tell you how to get that number necessarily, but it tells us in this case that for any function that's continuous, if you take the average value of the function from a to b, then you can always find a number c such that the function value there matches the average value of the function exactly. Okay, what do I mean by that? So in this example, I can draw a line, say, here. And let's say that this is the average value of my function. Okay, what does that mean? Again, it means that I can sort of take the areas that are above the red line and use them to fill in the gaps below the red line. Okay, so can I see from the graph here that indeed such a number c exists? So the answer here is yes, right? I just need to take this as my c, for instance. Because the function is continuous, you'll always be able to hit some point in the middle, or possibly at the ends as well, such that this function, f of x, crosses this red line that we have here, which is the average value of the function. And where it crosses it, these are the candidates for c. Like all of these points can be c's. And I'm not going to do this last question here, but go back to the particle in the first example with velocity function t squared plus 3. Can you find a point in the interval from 0 to 3 where the velocity at that point is equal to the average velocity, which was 6? All right, so try this yourselves.